Welcome back to Dave Does Maths from Home. We're still talking about line integrals. We're doing line integrals in 5 easy steps or your money back guaranteed. I have been advised by my wife, who is listening to me record this, that I shouldn't offer you a money back guarantee because that's just a thing I say because I think it's funny. I actually have no power to give you your money back for anything, really. So, let's all appreciate that that's just a joke. YouTube money back. There we go. Line integrals in 5 easy steps, or however much you paid to watch this video on YouTube, you can have that money back. Guaranteed. We'll go with that. Let's do some line integrals. The next example I want to do is I want to use another pretty straightforward vector field. So we're going to do we're going to use the explosion vector field, f of xy equals x comma y. So this is the vector field where everything is radiating outward. You get little vectors close to the origin. You get big vectors everywhere else. We all know about the explosion vector field. And I want to do along the path. Let's do along the line from -3, 1 to, let's go to 2, 3. Let's go to 1, 3. Let's do that one. Okay. So, in the last video, I promised that making a path out of a line was extremely simple, and it is, which is good because parameterizing this line is the first step when doing these line integrals. As we remember from our 5 easy steps. Step 1, parameterize the curve. If you're going to parameterize a curve like this, the parameterization is always pretty much the same. Make a vector that starts with your starting point. Our starting point is -3 on the x and 1 on the y. So this is going to be our starting point. And then we will add some multiple of t. So on the x-axis we want to go from -3 to 1. That's an increase of 4. So we're going to add 4t. On the y-axis we want to go from 1 to 3. That's an increase of 2. So we're going to add 2t. And then we're going to let t go from 0 to 1. So this -3, 1, that's your starting point. 4 and 2 are like your increase in x and your increase in y. If for some reason you have a decrease in these numbers, then just put in the negatives there instead. That works just as well. And then let t go from 0 to 1. It's foolproof. It works every time. So when you plug in 0 for t, these pieces are going to be ignored. You're just going to have the 3 and the 1. When you plug in 1 for t, you're going to get the 1 that you want here, and you're going to get the 3 you want here. So that's nice and clean as your endpoint. And then everything in between will be linear because you've got this thing set up as a line. So that's how we parameterize a straight line. This piece is our x. This piece is our y. We need to keep that in mind when we get to step 3, and we need to parameterize, or we need to express our vector field in terms of t. That'll be important. But right now we're not there yet. This is just step 1. We have our r. It's taken care of. Step 2, we need to find dr, that is the derivative of this, and that is going to be 4, 2. When you do straight lines like this, the dr you end up with is really simple. So that's nice. Dt. It's that thing that I always forget. I'm still forgetting it. Step 3 is we need to express this vector field in terms of t. So I don't want f of xy anymore. I want f of t. And f of t in this case is going to be, f was x, which is this stuff. So -3 plus 4t. And then y, which is this stuff, so 1 plus 2t. F actually looks a lot like R does. That will happen pretty much any time you ever use the explosion vector field. If you're using the explosion vector field, then it's already xy and R is xy, so that happens. But that's fine, the math still works. Step 4 is we need the dot product, f of t dot dr. The dot product here is going to be negative 12 plus 16t plus 2 plus 4t. And we can clean that up a little bit. I'm going to call this negative 10 plus 20t. This is the dot product of our vector field and tiny little chunks of our path. And that's step 4 finished. Now we need to do step 5. Step 5 is we integrate. So the integral of f of t dt, f of t dr, the vector field in terms of t across this path, over this path. This is the same as the integral. T is going to go from 0 to 1 of negative 10 plus 20t dt. I forgot the dt's again. There should be a dt here. In the next video, I'm going to forget the dt's and then just not even put them in until I write the integral. That's fine. So now we can integrate. This will be negative 10t. This will be plus 10t squared from 0 to 1. Is this just going to give me 0? That seems weird. Huh. I didn't actually finish this example problem before I made a video about it. So I'm a little surprised by this answer. This is going to be negative 10 plus 10, so yeah, that's 0. I guess this path, sort of straight across this vector field, negative 3, 1 to 1, 3. Because back here, the path should be pushing against it, and back here the path should be pushing with it. So maybe those things just cancel each other out? I kind of want to try doing this path using different starting and ending points to see if that changes anything. What?
Should you start over?
No, I'm good. This will be fine. Okay. Let's pick different points, see if we get an integral that isn't 0. Let's go straight up. Let's go from, or no, not straight up. Let's go from 0, 3, 0, 4. That's over here. Let's go from there to 5, 5. So the new path, it's all in quadrant 1. It's going to start right here, and it's going to go over here. We have a horizontal increase of 5. We have a vertical increase of 1. This is generally moving in the same-ish direction of the vector field, so we'll see if we get something non-zero this time. Step 1, parameterize the curve. We're going to make a big vector for r. We're going to start with the starting point, 0 and 4. And we're going to add the difference. So the difference on x is going to be 5t, the difference on y is going to be 1t, and this is r. T goes from 0 to 1. dr will be the derivative of this. That should just be 5 comma 1 dt. F of t, again, is going to look a lot like r, since this is the x coordinate of our path and this is the y coordinate of our path. We're just going to plug the x coordinate in here for x and the y coordinate in here for y, and we'll get something that looks exactly the same as r. 5t 4 plus t. Step 4, we need the dot product. F of t dot dr. That is going to give us 25 t plus 4 plus t. Seems fine. This is going to end up being 4 plus 26t. I bet this isn't going to give me a 0 answer when I integrate. Step 5, of course, is integrate. The integral over the curve of the dot product between the vector field and tiny little pieces of the path is the integral from 0 to 1 of 4 plus 26t dt, which is 4t plus 13t squared from 0 to 1, which should give me, I think, 17. What a weird collection of points I chose for that first problem. That was unusual. I didn't expect to pick the exact 2 points that would give me 0 net work, but apparently I did, so that's neat. So, now we can do line integrals along function paths, parabolas. And that technique in the last video we used for the parabola, that can work for any function. If you have a cubic function or a Wiggles function, doesn't matter. As long as you have the function expressed in terms of, or expressed as y in terms of x, you can always just replace your x's with t's, replaces your y's with your function of t's. That gets you a parameterization. All the steps follow from there. The thing that we still need to work on is circles. So, I have a moderately complex circles problem for us, but I'm going to start a new video for that one. So, stay tuned.